Welcome to the Deep Dive. Today, we are taking a deep plunge into, well, something many people might find a bit dry. Personal protective equipment, PPE.
And its more technical sibling, RPE, respiratory protective equipment.
Yeah, exactly. But we're not here to just read through regulations. We want to treat this like fascinating engineering. It's about the science of selection.
Right. We've got a pile of guidance docs here, regulatory stuff, practical advice. And the mission really is to give you, the listener, a shortcut.
A shortcut to what, though?
To understanding the real differences, why picking the right gear is so critical, and, the details that make protection actually work or fail completely.
Okay, so let's start with the basics. PPE, the official definition. It sets a specific tone, doesn't it?
It really does. Officially, PPE is all equipment intended to be worn or held, which protects against one or more risks. Standard stuff. But the kicker, it's almost always the last resort.
Last resort, meaning what exactly?
Right. Meaning, if you're relying on PPE, everything else, engineering controls, changing the process, better ventilation, it's either failed or it just wasn't possible in the first place.
So it's the final safety net.
Yeah.
And if that fails, the worker's exposed.
Precisely. That's why the stakes are so high and why suitable PPE isn't just a suggestion.
Okay, so what makes PPE suitable, according to these sources?
It's quite strict, actually. First, obviously, it has to be appropriate for the specific risk. That makes sense.
Right.
But it also mustn't increase the overall risk.
How could it do that?
Well, think about really bulky or hot gear. It could cause heat stress or make someone so tired they make a mistake. That's a new hazard introduced by the PPE itself.
Oh.
Then there's ergonomics. Got to be comfortable enough, has to fit the person properly, obviously meet the relevant standards, conformity markings and all that.
And you mentioned fit. That leads to compatibility, right? Like wearing multiple pieces together.
Yeah, that's a huge one, often missed. Say you need a hard hat, safety glasses, and a respirator. If those glasses push the edge of your mask just slightly, break that seal, well, you've basically bypassed the respirator entirely. Compatibility failure is a really common weak link.
Right. Makes sense. Let's zoom in on the lungs then, RPE. This seems like the most complex bit. The sources mention two fundamentally different approaches.
Absolutely. It boils down to how you get clean air to the lungs. Two main pillars.
Okay, what are they?
Pillar 1, respirators. These use filters. Could be a simple disposable mask, could be a powered unit, but the key is they remove contaminants, dust, fumes, vapors from the air you're breathing in. They purify the surrounding air.
Got it. Purifying the air around you. What's pillar 2?
Pillar 2, breathing apparatus, or BA. This is completely different. BA doesn't filter the local air. It supplies clean, breathable air from a totally separate, uncontaminated source. Think scuba gear, but for work.
Okay, supplying clean air versus filtering dirty air. Let's dig into the respirators first. The difference between non-powered and powered sounds like a big deal. What's the issue with basic non-powered masks?
The main drawback with non-powered ones, like your standard dust mask or a AF mask with cartridges, is that you have to do the work. Your lungs pull the air through the filter.
Okay.
So when you inhale, you create negative pressure inside the mask, a slight vacuum.
Ah, and if the fit isn't perfect, or there's a tiny crack.
Exactly. That negative pressure becomes a suction point. It pulls the contaminated air in through any leaks, bypassing the filter completely. That's why fit is absolutely critical for these masks.
So a tiny gap basically makes the mask useless.
Pretty much, yeah. Especially with really hazardous stuff.
Okay, so if negative pressure is such a problem, how do powered respirators fix it? What's the trick?
The trick is simple but clever. They flip the pressure. Powered respirators have a battery-powered fan or pump that pushes air through the filter and into the mask.
Ah, so instead of sucking?
It's blowing, gently. This creates positive pressure inside the facepiece.
So now, if there's a small leak, clean filtered air blows out.
Precisely. It actively resists contaminants trying to get in. It's a massive safety upgrade. Plus, it makes breathing much easier, reduces fatigue, so people can often work longer.
Right, that makes a lot of sense. Okay, switching gears to breathing apparatus, the supplied air route. You mentioned tethered systems and self-contained ones?
That's right. The tethered ones, or supplied air systems, have a couple of types. There's the basic fresh air hose BA. It's literally just a hose running to clean air, unpressurized, usually limited to maybe 20 meters.
Simple enough. What else?
More common is the compressed airline BA. This uses, compressed air from cylinders or a special compressor, allows for much longer, smaller hoses, maybe up to 80 meters.
But if it's coming from a compressor, Isn't there a risk of oil or contaminants from the machine itself?
Huge risk. That's why inline air filters are non-negotiable. They have to purify the supplied air to make sure it's safe to breathe, remove oil mist, dust, rust, even nasty gases like carbon monoxide if the compressor intake is badly sited.
Okay, and within those, you can have different airflows.
Yeah, you've got constant flow, which just pushes air in continuously, and demand flow. Demand flow is smarter. It only supplies air when you actually inhale. Saves air, especially with cylinders.
Makes sense. And then the ultimate mobility, self-contained breathing apparatus, SCBA, where you carry your air supply with you.
Right. SCBA is for when you need total freedom of movement, or maybe the escape route isn't clear. We usually categorize these by how long they last.
Okay.
You've got short duration escape SCBA, maybe 10, 15 minutes, just enough to get out fast if an alarm goes off, often used with gas detectors.
Right, for emergencies.
Then the workhorse, general SCBA, usually designed for around 30-40 minutes of work. These are typically positive pressure, like the powered respirators for that extra safety margin. Think firefighters.
And the really advanced stuff.
That would be the recirculating SCBA or rebreathers. These are closed circuit. They actually scrub the carbon dioxide from your exhaled breath, add a little fresh oxygen, and let you breathe it again.
Wow. How long can those last?
Hours, sometimes up to 3 hours or even more. Essential for things like mine rescue, long tunnel entries, complex hazmat situations.
Okay, but underlying all of this RPE discussion, there's that one absolute rule about oxygen.
Cannot stress this enough. If the air doesn't have enough oxygen, generally below 19.5% filters are completely useless. A filter cannot create oxygen.
So in oxygen-deficient atmospheres,
only BA-supplied air is acceptable. Full stop. You need to bring your own safe atmosphere with you.
Okay, that's crystal clear. Now, how do we actually choose the right level of protection? This is where that term APF comes in, right? Assigned protection factor.
Exactly. APF is the key metric. It's basically a number that tells you how much cleaner the air inside the mask is expected to be compared to the air outside.
So a higher APF means better protection.
Much better, yeah. It's a ratio. APF 10 means the air inside should be 10 times cleaner. APF 1000, 1,000 times cleaner.
Okay, let's make that practical. Sources give an example, right? Using the workplace exposure limit, the WL.
They do. Let's say the WEL for some nasty vapor is 20 parts per million, 20 ppm. That's the legal safe limit over an 8-hour day.
Okay.
But you measure the air in the work area, and it's actually 160 ppm, much higher.
Right. So how do you figure out the APF needed?
Simple division. You take the measured level, 160 ppm, and divide it by the safe level, the WEL, 20 ppm.
160 divided by 20, that's 8.
Correct. So the minimum required APF for the RPE in this situation is 8.
But you wouldn't just aim for the minimum, would you? That only gets you down to the legal limit.
Exactly. In practice, you'd always build in a safety margin. You might choose an RPE with an APF of, say, 20 or even 40 in this case. You want to be well below the limit, not just scraping by.
And APF isn't the only factor in selection, is it?
Oh, not at all. You have to consider the substance itself, obviously. The task, how hard are you working, for how long, do you need to move around, and then wearer factors, too.
Right. And the biggest wearer factor seems to be, does it actually fit? All the APF ratings in the world don't matter if the mask leaks, right?
Right. Fit is everything. Particularly for those negative pressure, tight-fitting masks we talked about. Decades of research show that a mask that should give you, say, APF 10 might give you personally much less if it doesn't seal perfectly to your face.
Because everyone's face is different.
Exactly. Mass production versus individual faces. That's why for most tight-fitting RPE, a face fit test isn't just recommended, it's often legally required.
What about things like loose-fitting hoods or helmets, the ones with powered air? Do they need fit tests?
Generally, no. They rely on flooding the hood with so much clean air, that positive pressure concept, again, that minor leaks don't matter as much. The high airflow keeps contaminants out.
Okay, so for the tight masks, how do they do these fit tests? Are there different kinds?
Yeah, 2 main types. First is qualitative testing.
Qualitative, meaning quality, not quantity.
Right. It's basically a pass-fail test, subjective. They put a hood over your head while you're wearing the mask, then spray a harmless but strong-tasting or smelling substance inside the hood like a bitter solution.
And if you taste it?
You fail. While spraying, you do exercises, move your head, talk, bend over things that might break the seal. If you taste it, the mask doesn't fit you properly. But this only really works for half masks or a disposable respirator.
I only those.
Because it relies on you noticing the taste or smell. And it doesn't give you a number, just a yes-no.
Yeah. What if you have a cold or just can't taste that bitter stuff well?
That's the weakness. which is why for full face masks, or where the hazard is really serious, you need quantitative testing.
Quantitative giving a number. How does that work?
It uses a machine, often a particle counter. It measures the concentration of microscopic particles outside the mask and compares it directly to the concentration inside the mask while you do those same exercises.
Ah, so it removes the guesswork.
Completely. It gives you a numerical score called the fit factor, which tells you exactly how well that specific mask fits that specific person, much more reliable.
Okay, the seal is clearly king for lung protection. Let's shift to the skin and eyes. Gloves, for instance. It's not about filtering air anymore.
No, with skin contact, especially chemicals, it's all about resistance. And just grabbing the thickest glove isn't always the answer. You need to understand 3 things about how a chemical interacts with the glove material.
Okay, what's the first one?
Breakthrough time. This is crucial. It's how long it takes for the chemical to actually soak through the glove material at a molecular level, not just through a pinhole, but permeating the material itself.
So even if the glove looks perfectly fine,
The chemical could already be on your skin if you've worn it past its breakthrough time for that specific chemical. Good gloves might list times like 240 minutes, 480 minutes.
got it. What's number 2?
Permeation rate. After breakthrough starts, how fast does the chemical move through the material? You want a low rate, obviously.
Right.
A long breakthrough time and a low permeation rate is the goal.
Makes sense. And the third?
Degradation. This is about how the chemical physically attacks the glove material itself. Does it make it brittle, swollen, gummy? A degraded glove can split or tear easily, leading to massive exposure long before chemical breakthrough would have happened.
And thinking about thick gloves, that brings up another issue, doesn't it? Dexterity.
Ah, yes, the classic dexterity dilemma. It's a constant trade-off. Thicker materials usually mean better chemical resistance and durability, but you can't feel anything, you can't grip small things.
Right.
And the sources actually highlight this. In some chemical handling tasks, like dispensing very small amounts, say less than half a liter, wearing really thick, clumsy gloves might actually increase the risk.
How so?
Because you're more likely to fumble, drop the container, cause a much bigger spill than if you had better control. Sometimes the guidance leans towards maybe thinner gloves with quick removal and washing, or even careful barehanded work if the risk assessment supports it and washing facilities are immediate. It sounds counterintuitive, but it's about the overall risk.
Wow. Risking a bigger accident because the protection makes you clumsy. That's a key insight. Okay, let's quickly cover eyes. What's the progression there? From basic to serious protection.
It's a hierarchy, like RPE. You start with basic safety spectacles. Good for low-energy impacts, like from chipping or grinding, maybe some UV protection.
But they have gaps, right?
Yeah. The big drawback is they don't seal. Stuff can still get in around the sides, top or bottom, so not great for dust or splashes.
So for that, you need
Goggles. Goggles create a seal around the eyes, much better for dust, chemical splashes, that sort of thing. They can have different ventilation types depending on the hazard: direct vents for impact, indirect or capped vents for liquids or chemicals.
and the top level.
Face shields or visors. These protect the whole face, not just the eyes. Essential for things like handling large volumes of corrosive liquids where a splash could hit your forehead or chin, or for intense heat or radiation like in welding. Often worn over goggles or spectacles for combined protection.
Okay, so we've got the gear, the science of selecting it, the testing. But what about the person actually wearing it all day? The human factors.
This is where the best plans can fall apart. If people don't or can't wear the PPE properly, it's useless. And the sources flag several key issues.
Like what?
The biggest one for pipe-fitting respirators: beards.
Ah, yes.
Any facial hair, even stubble sometimes, that lies under the seal area makes a proper fit impossible. Just can't happen.
So what's the solution? Clean-shaven policy.
Often, yes. For areas requiring tight-fitting masks, employers might have to enforce a clean-shaven policy or provide those loose-fitting powered hoods instead, which don't rely on a face seal. But you can't just ignore it.
What about people who wear glasses, prescription glasses?
Another big one, especially for full-face masks or SCBA, the arms of regular glasses break the seal where they pass through the rubber.
Right, so you can't wear your normal specs.
Nope. You need special spectacle inserts that mount inside the mask visor. They don't have arms going over the ears, so the seal stays intact. Employers need to provide these if workers need vision correction.
And then there's general compatibility again. Hard hats, ear defenders, maybe religious head coverings.
All have to work together. Can the hard hat be worn comfortably over the respirator straps? Can ear defenders fit without dislodging goggles? Can a head covering be worn without compromising the RPE seal? It all needs checking.
And ultimately, will people actually wear it?
That's wearer acceptability. Is it reasonably comfortable? Does it fit well? Does it interfere massively with doing the job? If the answer is no, people will find ways not to wear it or wear it incorrectly.
So involving workers in trials and selection helps.
Hugely. If they have a say in choosing gear that works for them, they're far more likely to accept it and use it correctly.
And fundamentally, the responsibility for getting all this right lands on
The employer, absolutely. They have the duty to provide suitable PPE, free of charge, and crucially, to maintain it. Cleaning, checks, storage, replacement parts.
and training too, presumably.
Yes, proper information, instruction, and training on why it's needed, how to wear it, how to check it, its limitations. And it has to be in a form people actually understand. Language, complexity, all needs to be right for the workforce.
Okay, that brings us pretty much full circle. A lot to take in. Let's try and summarize the big takeaways.
Yeah, I think number one is that core difference. Respirators filter the air and worry about negative pressure leaps unless they're powered, while breathing apparatus supplies clean air, essential if there's no oxygen.
Right. Second takeaway, selection isn't guesswork. You need the science of the APF, the assigned protection factor, calculated based on the actual exposure versus the safe limit.
And third, even with the right APF, it's useless without a proper fit. Hence, fit testing for tight masks and dealing with those human factors, beards, glasses, compatibility, comfort.
It's that last line of defense, and it has to be solid.
Which leads to a final thought. The sources mention RPE, especially things like SCBA sets, are often shared between workers. They're safety critical, yes, but also intimately worn.
Yeah, hygiene must be a factor.
A huge one. Proper cleaning, disinfection, maintenance records. It's not just about preventing mechanical failure. It's about preventing cross-infection or even sensitization to materials like latex in the masks between users. How well is that actually managed? How much trust do you place in the hygiene of shared life-saving equipment?
That is definitely something to think about. How clean is that last resort? Okay, that's all we have time for on this deep dive.